Welcome to the lecture on single and double slit diffraction. Upon successful completion of this unit, you should be able to describe and calculate single slit diffraction, describe the conditions necessary for single slit diffraction compared to double slit diffraction. When you shine red laser light into an opening that is only 0.1 millimeter wide, it does spread out and it forms an interference patterns of light and dark bands. The diffraction of light is observable if the hole is sufficiently small. This means that red light has a small wavelength. I told you in the previous lecture that you can actually see this for yourself. So you can go back and look at this and try it yourself. Single slit diffraction. When diffraction through a tall, narrow slit is known as single slit diffraction. A viewing screen is placed at distance L behind the slit of width A, and we're always going to assume that L is much greater than A. Now, this is a review of Huygens' principle. Each point on a wave front is the source of a spherical wavelet. Together, these wavelets will spread at the speed of light. They will create the next wavefront. The new wavefront is tangent to all of the wavelets. The new wavefront, in turn, is the source of an infinite number of wavelets that creates the next wavefront. Now, this is not strictly correct. The model is still useful for visualization purposes. We can also apply this to spherical waves. As with plane waves, each point on a wavefront is a source of new wavelets. These wavelets propagate at the speed of light and create the next wavefront. The new wavefront is tangent to all the wavelets, and the new wavefront, of course, is a source of an infinite number of new wavelets. Now, as a wavefront passes through a narrow slit of width A, each point on the wavefront, right here, can be thought of as the source of a spherical wavelet. The new wavelets spread out, overlap, and interfere with each other. This creates a diffraction pattern of alternating light and dark bands that we see on the screen. Now, shown here are the paths of several wavelets. Okay, here's a slit right here of width A. Shown here are the paths of several wavelets that travel straight ahead to the central point on the screen. The screen will be way off to the right. The paths are very nearly parallel to each other, thus all the wavelets travel the same distance and will arrive in phase at the screen. This creates a bright central maximum in the center of the diffraction pattern. The width of the slit must be greater than, but on the order of the size of the wavelength of light. If the slit is not the correct size, the pattern of light and dark bands will not appear. Okay, so here's what happens when the light is coming out from an angle. In this picture, these are pairs of wavelets. So wavelet 1 and 2 are a pair, and those wavelets start from points that are a/2 apart. Every point on the wavefront is paired with another point at distance a/2 away. So 3 is paired with 4, and 5 is paired with 6. If the path length difference is delta r equals lambda/2, then the wavelets arrive at the screen out of phase and interfere destructively. And if you look here, here's the path length difference right here. This is delta r. Notice here's the angle. That's the same angle here. And this is a/2. So delta r is a/2 times the sine of theta 1. And that has to equal lambda/2. Together, these create the pattern of dark fringes on either side of the central maximum, which are located at a sine theta 1 equals lambda. Okay, now the resulting light from a single slit consists of a large central maximum or strong central maximum flanked by a series of weaker secondary maxima and dark fringes. As it turns out, we can only accurately locate the dark fringes, which occur at angles of theta p equals the inverse sine of p lambda/a. If the small angle approximation is valid, that is, theta is less than 5 degrees, the dark fringes are located at the angle of theta p equals p lambda/a for theta p in radians. Be careful with that. The bright fringes are located approximately halfway between the dark fringes. So P, of course, here is where the dark fringes are located. It's kind of like the order number. And this is the width of the central maximum right here. That's W. And, of course, this is L, and that's A. Okay, warning. This formula strongly resembles the one for the double slit one that locates the bright fringes. But this one locates the dark fringes, so be careful with that. Now, as you change the slit width, this is what happens. As the slit width increases, here's A is approximately equal to the wavelength of light. Here A is 5 times the wavelength of light. Here A is 10 times the wavelength of light. So the central maximum grows sharper. That has decreasing width. This indicates less flaring out of the light. The secondary maxima also decrease in width and strength. Eventually, if we make the slit very wide, the secondary maxima disappear entirely, although the light is still diffracted at the edges of the slit. That's not shown here. If we make the slit very narrow, again, only the central maximum appears, and it expands to fill the screen. Okay, light from a helium neon laser with a wavelength of 600 33 nanometers, passes through a narrow slit and is seen on a screen 2 meters behind the slit. The first minimum in the diffraction pattern is 1.2 centimeters from the central maximum. How wide is the slit? Well, the physics of this is a single slit, and we can use the small angle approximation. We know the wavelength of the light. We know the distance between the slit and the screen. We know y1, first minimum of the diffraction pattern. And we know p equals 1 because it's y1. And what is a? So theta p will be p lambda over a, and s equals theta r. And yp will be theta p L, where theta is in radians. And the algebraic solution for that is theta p equals p lambda over a, or yp over L. And therefore, a has to be p times lambda L over yp. Now we can plug our numbers in. When we do that, we plug in our wavelength, converting everything to meters, our L, which is the distance between the screen and the slit, and yp, which is the first minimum of the diffraction pattern, where that's located on the screen. It turns out that the slit width is 0.11 millimeters. We can check that by figuring out what theta p is. Theta p will be 0.00122 divided by 2. And what we're doing is we're checking to make sure that the angle is small. It's quite a bit smaller than 5 degrees, so we're safe. This is a central maximum of a single slit diffraction pattern. Notice that the central maximum is the one that's really bright. The other ones are kind of dim, and they get dimmer the further you go out. The width of the central maximum on a screen, a distance L away, is twice the spacing between dark fringes on either side. And of course, that equals 2 lambda L over A. The further away from the screen you go, the larger L, the wider the pattern of light becomes as expected because it spreads out. The narrower the opening, the smaller the A, also the wider the width of light. So in other words, as you narrow the opening, the diffraction increases and it spreads out even more. Eventually, if you spread it out too far, you don't get anything. A laboratory experiment produces a single slit diffraction pattern on a screen. If the slit is made narrower, the fringes will widen out. They'll move further apart because YP and A are inversely proportional to one another. Light passes through a 0.12 millimeter wide screen and forms a diffraction pattern on a screen 1 meter behind the slit. The width of the central maximum is 0.85 centimeters. What's the wavelength of the light? The physics of this is a single slit diffraction. We know A, we know L, we know W, but when we want to know lambda, so W equals 2 lambda L over A. We solve it for lambda. Lambda equals WA over 2L. Now we can plug in we have to convert everything to the same units, and I strongly suggest meters on this, 0.0085. Here's our 0.00012, that's our slit width, and of course 2 times L. When you crank the math, it ends up being 510 nanometers, and we can check to make sure that everything's okay. The angle is W over L. It is much less, way less than 5 degrees, so you don't have to worry about that one. We sort of kind of waved our hands at what the double slit diffraction pattern looks like. Reality is a lot more complicated than that. In the double slit experiment described previously, it was assumed that the slit width was much less than the separation between the slits. In other words, A is much less than D. What if this is not the case? And that's usually what it is not the case. Well, here we have an interference pattern for 2 vanishingly narrow slits where A is much less than D. Here we have a diffraction pattern for a single slit. Can you sort of see if you add these two together, do a little bit of magic in your head that you wind up with this? It turns out this is the envelope for this. You haven't changed the fringe locations, but you do lose some fringes. Where these minimums occur, you lose some fringes. Now the intensity formula for this is I equals IM cosine squared beta sine alpha over alpha quantity squared. This is the interference pattern. This is the diffraction pattern. And of course, A is the slit width and D is the distance between slits. Here's a picture of this. Here is a single slit. Here is a real double slit. Notice the little tiny maximum and minimum that are inside this double slit pattern. And this is because the real diffraction pattern you see is the combination of that produced by this double slit, that's one, and that produced by the slit itself. The lower part shows the interference pattern for a real double slit. The width of the slits is not vanishingly narrow. This is composed of the diffraction pattern of a single slit of width A, that's the upper picture, imposed on the interference pattern for the double slit down below with an infinitely narrow slit. And of course, that'll become the envelope. Only the intensities are affected. The location of the fringes is not affected. That's a good thing. The diffraction pattern below arises from a single slit. If we were to sharpen the image that makes the central spot narrower, what should we do with the slit width? Well, you're going to have to correspondingly widen the slit width. because to make W smaller, you want to increase A. A violet light of wavelength lambda passes through a single slit of width A and forms a diffraction pattern on screen. If the violet light is replaced by a red light of wavelength 2 lambda, the original diffraction pattern can be reproduced if the slit width is changed too. If you double A, you need to double lambda to keep the same pattern. Which of the following must be satisfied if interferences occur for light passing through a single slit? The width of the slit must be comparable to the wavelength of light. Thank you.